Hi. True story. I thought this talk was on Friday, so the last couple hours were a little fun. But I mostly had the slides together before, so let's have some fun with GeoArrow. So first, I want to assume that you don't really know anything about Arrow or GeoArrow or any of that. And just step back and ask, like, why Arrow? Why has Arrow been a popular technology in the last few years, and why should we care? So data serialization is really expensive. Arrow is a cross-language technology, but for this example, to motivate why you should care, this is focused on Python. And let's say that we want to create a Python library and we want to integrate with Shapely. Well, Shapely has its own way of storing data, and so in order to access the data from Shapely, we need to do serialization between the Shapely library and our library. And so here, we are setting up some data of just loading an example data set from the GeoDatasets library and getting a Shapely multi-polygon geometry. This is actually Staten Island in New York. It's just a kind of complex multi-polygon. And so in Python, there's already a protocol for sharing data called GeoInterface, which is essentially an attribute on a class that, if you access, gives you a GeoJSON-like Python representation of your data. Oh, okay. And that works and is convenient, but it is a little slow. And so in this case, this takes 3 milliseconds to just serialize this geometry object into a GeoJSON string, and takes about 345 kilobytes. You might not think that that's too slow, but that's one single polygon, and so that'll take more time for other geometries. And it has 2 full memory copies. And so you could speed that up by doing binary serialization instead of GeoJSON. And so in this case, this is now 15 times faster than using GeoJSON, and it's a lot smaller than a string serialization, but it still requires 2 full memory copies to serialize from the source data representation, and then to parse into whatever representation your target library wants to use. And so ideally, we could set up some format that, instead of having to do this copy and convert from one library to another, we could have both libraries understand the exact same underlying data representation, so that you can share the existing data. And so in this case, we are using GeoArrow to to exchange data between 2 different Python libraries. This last line, the pyarrow.array line, is moving the data from the GeoArrow library into pyarrow, and that takes 6 microseconds, which is 30 times faster than the previous slide. But the thing is, this is constant time instead of linear time, and so that means that if you take 1,000 geometries, then that takes 1,000 times longer when you're serializing the data. But with Arrow, because there's no data copying happening, it's actually the same exact time. So in this case, with 1,000 geometries, what previously was 30 times faster when you have 1 geometry, if you have 1,000 geometries, is now 35,000 times faster. And so you get these graphs, like in the bottom right. This is from a blog post on using Arrow to move data between R and Python. And when historically you would use like JSON to move a data frame between R and Python, you would get this linear graph with more and more data. Well, it takes longer to exchange data between different systems. But with Arrow, because you have these 2 different systems that understand the same underlying representation, it is literally instant. It has a little bit of overhead to exchange, this is where the data is and this is the data types. But otherwise, it is essentially free to do that exchange. And so to motivate this, I actually want to talk a little bit about the history of what people have done before with data exchange, first starting in Python. So NumPy came about. NumPy 1.0 was released in 2006. And NumPy is just like the canonical library for doing any sort of scientific programming in Python. And they started to build this ecosystem around NumPy where there was SciPy created and other scientific libraries that wanted to access NumPy's data. But if you had that same problem as before, where, well, if I have to make copies and figure out some sort of serialization, then it's really slow and it impedes this sort of decentralized progress and innovation around NumPy. And so the Python buffer protocol was created in 2008, which is essentially just a specification for here is an array, and here is how some other library can understand that array at a low level without having to copy the data. And so Jake Vanderplas, who wrote the Python Data Science Handbook, which is actually like one of the books I learned how to write Python with, was like, the buffer protocol is really like what makes Python what it is today. All of the AI and everything like is relying on top of NumPy and being able to exchange data at a low level without cost. And so that made a lot of progress. And then a few years later, there was Pandas. And so Pandas was built on top of NumPy to have tabular data instead of just array data. And if you look at the documentation for Arrow, you'll see these images on the right-hand side where the names are kind of dated, like Kudu and HBase. I don't really know what those are, but in 2015, people cared about those. And there was all these different libraries and databases that wanted to exchange data with one another. And in Python, you had R and Python, and you maybe wanted to have visualization with ggplot2 in R, but have some other stuff that was better implemented in Python. And it was really, really hard to exchange that data. And so Arrow came along and related projects like Feather that made it 1,000 times faster to move this data between R and Python. And so what Arrow is this specification that any language can implement, but that all of these languages interpret the same memory as this is how a table is structured, so you don't have to do that copy and serialization. Arrow has really become the standard for essentially all of these modern database or data frame-like tools that you might be aware of. So in Python, there's Pandas, Polars. DuckDB mostly uses Arrow internally and then has this Arrow export for exchanging with other systems. Even GPU has cuDF from NVIDIA for essentially putting Arrow on the GPU and using data that way. This is from before, that data movement is always constant time, no matter how large your data is. Well, in Geospatial, we essentially have that same problem as what Pandas had before, where we have all of these different libraries, QGIS, GeoPandas, Sedona, GeoParquet, whatever, that people want to use all of these libraries together. And that was pretty difficult when you had to use maybe GeoJSON, or it would work, but it would take a long time and use a lot of memory. And so GeoArrow extends Arrow with some of the built-in Arrow extension points where you can define a way to store geospatial vector data in Arrow. And so that makes it a lot easier, because instead of implementing like this M by N approach where every library needs to support every other library, you only have to really support Arrow efficiently, and then you get really efficient transfer with all of the other libraries as well. So if we dive into how GeoArrow is actually implemented, at a basic level, vector data has points, line strings, polygons, and then features defined as the geometry plus some attributes. Well, we can store that data in a table In this case, I made this for GeoParquet, but GeoParquet and GeoArrow are actually like the exact same under the hood, where GeoParquet is as a file, but GeoArrow is in memory, where you have a geometry column and you have attribute columns. And so this has these chunks of arrow memory in a table that GeoPandas or anything like this has attributes and a geometry column. And so all of those columns are arrow now, where one of those is defined as this GeoArrow column that has GeoArrow metadata. And so GeoArrow, the specification itself, defines how to use the existing arrow types to store geospatial data. So there are raw native layouts, and so that native just means that it is you're able to access the coordinate buffer at the low level without having to do any additional parsing. And so we'll see, like in Lonboard, on some talks on Friday, for visualization, we can use that to have really fast plotting because we don't have to parse the well-known binary. But similarly to GeoParquet, well-known binary is often used as just like everybody understands well-known binary. So GeoArrow supports both, kind of this faster way to represent geometries for programs that can support it, as well as historical fallbacks or serialized fallbacks for well-known binary and well-known text. So if we look at how points are actually represented in GeoArrow, we have this struct column that is one column that has named children X and Y. And so if we have points 0, 0, 1, 1, 2, 2, then we have an array of all the X's and an array of all the Y's. So that's pretty simple. If we extend it to polygons, then the GeoJSON logical representation of this polygon is, you can think of as these coordinates. For GeoArrow, all of the coordinates in a row, and all of the coordinates actually in the entire column, are in a contiguous array. And so here we have this X array that has all of these coordinates, and then we'll have any of the other coordinates in that column. And then we have these offsets array. And so that is how you can look up which coordinates are part of which ring by finding the coordinates that are sliced between index 0 and 5 is part of the first ring of the polygon. And then which rings are part of which polygon. So here, the 0, 2 at the bottom means that the first two rings are part of the first polygon. You don't have to really understand this low level unless you're implementing the data or implementing some low-level program to support it. But just know that it allows you to have really fast access to raw coordinate data in a way that you can share between different libraries and languages. So we recently released GeoArrow 0.2, which has support for all of these different canonical basic types, where if you have a column of points, that means that you can only have points in that column, which is most space efficient, because you don't need to have all of this other data for, oh, is this a point, is this a polygon? It's just points. We also have mixed type columns now, so you can support generic geometry columns, geometry collection columns. You can support rectangles or boxes, as well as these serialized well-known binary representation. And we have metadata so that you can persist coordinate reference system or something like that. If we actually look at the exchange in practice, GDAL is one of the first implementers of the GeoArrow specification, where historically the way that GDAL worked was it had this getNext feature API where you would call that iteratively and you would say, okay, I have 100 rows, well, I'll have a for loop that is called 100 times, or 100 iterations of the for loop, where GDAL is loading this data, and then Python iterates over the getNext feature API. But that was pretty slow, because if you do that iteration in Python, then Python as we'll see in some benchmarks in a second, is slower to do this this loop than native code. And so when GDAL added this arrow support under the hood, that means that this is moved outside of Python and thus becomes a lot faster. And so GDAL added this in 3.6. And now as we move into some benchmarks, this is the first benchmark. This is looking at just using Fiona versus Pyogrio, where Fiona and Pyogrio are two different backends that both connect to GDAL. Pyogrio is a lot faster than Fiona, but this so far is the Pyogrio native implementation that does a lot of really complex C code to manually connect to GDAL and create the arrays by hand. Once you use the arrow support in GDAL, it becomes even faster. And this was actually like 10 lines, maybe 100 lines of code, but very, very little code that Pyogrio has to write and maintain, because instead of exposing, GDAL was essentially exposing GeoJSON for each row, and that's really slow to iterate over that in Python. Here, this is even faster and even easier to do from the Pyogrio side. This is a little confusing because the colors switched, but now blue is with the Pyogrio API, and orange is with the Pyogrio Arrow API. And these are still loading into GeoPandas, which has to do the additional work of loading and parsing into Shapely. If we avoid even having to parse into Shapely, then it gets even faster. So if we look at the Geo package, historically, if we used Fiona into GeoPandas, that was taking 140 seconds. And now if we just want a table from this Geo package and we're okay with it in this arrow layout, then that takes like 1.5 seconds. And so that's a huge, massive performance improvement. And so if we, ideally, if you're ever using GeoPandas to load data, you should always use engine equals Pyogrio, use arrow equals true. I think that engine equals Pyogrio is now the default, but use arrow is not the default yet in GeoPandas, because it didn't want to require an arrow dependency for everybody to use this. But for all intents and purposes, you should always pass use arrow equals true, and that'll make your operations a lot faster and support some stuff like timestamps a little bit better. So if we actually look at this, we can use a couple different of these libraries. So GeoArrow Rust is a library that I develop. We can load the flat GeoBuff file, for example. And here, this is a arrow table that is loaded by GeoArrow, Rust, this flat GeoBuff representation. And then we can use the GeoPandas geodata frame from Arrow API, and that converts the Rust handle on the data to a GeoPandas handle on the data. And so the from Arrow is really easy to pass any sort of Arrow data consumer into that API. And on this side, we can have we can do the same on the other or that's not the other direction yet. GeoPandas, we can connect to DuckDB, where here, DuckDB, this is not the default yet, but I think in the next version, 1.5 of DuckDB, this will be the default where you won't even have to call register extensions. If we go towards the ecosystem a little bit, I have 1 minute left. Okay, yeah. So there's several different GeoArrow libraries in Python with either from the Rust bindings or the C bindings, and Rust, C, TypeScript, R. I want to point out that there is actually 3 talks on Friday. I'm giving one of them. 2 of them are on Lonboard, this library I developed that connects Python to DuckDB for visualization. And kind of spoiling part of the talk, but like this is like why GeoArrow matters at a high level of like, well, this was PyDeck is the orange line, and Lonboard is the green line, and almost all of that is GeoArrow, of like using GeoArrow efficiently gave like 40 times performance improvements. And so this is a Python API, and then there's a JavaScript API for using GeoArrow on the web natively. And then there's a broader ecosystem now of tools that are supporting GeoArrow in Python and other languages. And so Whereabouts released SedonaDB recently that uses GeoArrow under the hood and allows you to, so for example, there are examples with SedonaDB and DuckDB where you can pass that data into Lonboard, and that is instant to move that data between these libraries because of these data movement techniques that we discussed at the beginning. This is also some of the beginning of this I wrote up in a blog post, actually, of making performant Python bindings to compiled code with the link there, where I talk about really like two different pieces of how you can speed up compiled Python code. And that's where I talk about the history of the buffer protocol and stuff like that. I go into a little bit more detail of how we can avoid the serialization overhead in this blog post. So you maybe check it out. And I think that's probably a good time to stop and ask questions.
Thank you very much, Kyle. Do we have any questions? All in the front row. Let's start.
I was wondering if we have some sort of, would it be geopolars? Being a Rust user,
yeah,
I would love that.
Well, okay, so the question was on geopolars. So polars is a fast Rust-based, Rust and Python data frame library. I prototyped geopolars a while ago, and it sounds like polars is implementing the required extension changes to be able to support this in polars. So hopefully soon we'll get support. But even if you're already using Rust, you can use a lot of the GeoArrow RS library without having to wait for that. Yeah, so there's also Polars SD. I don't know if they have Rust bindings. Oh, they do? Interesting. So Polars SD is a little bit different because they store the CRS. They only support well-known binary and extended well-known binary. And then they have to parse that extended well-known binary data every time they do an operation. So pass that to Geos, parse it, do an operation, and then create another well-known binary. And so it works, ideally, with some extension API improvements on the Polar side, we can support native GeoArrow stuff.
Yeah, so this is great. GeoParquet types have been merged into the core spec.
Yeah.
So I'm wondering, is there an intent to try to extend or get this into core Arrow, or if not, why not? What's the advantage to having something separate?
I think there's a little, so so the question is like, is it possible to, or because Parquet now has a native type for geometry, does it mean Arrow should have a native type for geometry? But Arrow has a little bit nicer extension points, so there's not necessarily a need for Arrow to support like canonical geometry type, because as long as they say this is the extension to use for geometry, it's a little bit less of an issue than it was on the Parquet side. I don't know if that was a good answer to the question, but right now, like having it as a well-known extension is probably where it's going to end up. I think it's.
My question was going to be the same. It was like the geospatial isn't special, idea. But I'll ask another question instead. Just so I understand, does Arrow basically replace the Python buffer protocol then? And does NumPy use that? Should it?
It's an interesting question. First on Arrow or Geo isn't special. One of the really cool things about Arrow is that if you have GeoArrow metadata on a column, you can use any library that knows Arrow, and as long as they persist that metadata, you can access that geotype. That geotype isn't lost once you move it to any library that understands Arrow, as long as they support the extension metadata as they should. And then, shoot, what was the second part of it? Oh, Python buffer protocol. Yeah, so the Python buffer protocol is really focused on n-dimensional arrays, and so it's focused on NumPy-like data. Arrow is mostly focused on this tabular data, like you imagine as in a database table, and so they mostly focus on two different things. There has been some talk about having NumPy integration be a little bit better, but for now they are mostly solving similar but different goals.
Okay, we'll have one last question, and then we'll move to the break. Bring your mic.
So from GeoPandas, using Arrow to load my data will give me speed, and then is it effectively instantaneous to turn it into a GeoPandas dataset?
Yeah, so that's what this graph is essentially trying to compare. So if you look at the orange versus the green, the orange is loading GeoArrow plus converting it to GeoPandas, and then the green is just loading it as GeoArrow. And so there's a little bit of overhead because GeoPandas works on shapely geometries. And so shapely, you need to do that copy and convert step to create those shapely geometries. And it's faster with GeoArrow, but you still have to do that serialization and deserialization. So it would, ideally in the next few years, there will be more and more tools that directly operate on GeoArrow without having to do this deserialization to shapely step. Or in the future, it would be great to have better native Geos to Arrow integration. So.
All right. Thank you very much, Kyle, again.